Hello. We are now going in this session to work through exercise 3 and 4 from homework 1. And exercise 3 is mostly Python, and exercise 4 is mostly mathematics. So let's start at exercise 3. We get to know some information about the empirical average and the empirical variance, which I believe you know from before. And then we are asked in A to simulate 100 standard normal numbers. So let's do that. First I import this NumPy package. And then I simulate 100 standard normal numbers with this random normal function in the package NP. The arguments 0 and 1 is the mean and the standard deviation, and 100 is how many we are, and the argument 100 is how many numbers we are asking for. So let's do it. So now x is an array of 100 numbers, and then we are told to make a new variable tilde x, which should be these x's minus the mean of the x's. So then we make this variable tilde x, which should be x minus the mean of x. So let's do it. There we got that one. And then we are asked to verify that the mean of this new variable tilde x is equal 0. So therefore I make mean tilde x and take the mean of tilde x, and we should get 0. Let's see. Yes, we get almost 0. 4.27 e in minus 17. Would it be like this every time? If I draw new numbers, new 100 numbers, let's do it and see if we get 0 again for the mean of tilde x. Yes, we do. It's not exactly the same number as last time, but it's almost the same, and it should actually be the same if the machine could calculate totally correct. Because we mathematically can show that mean tilde x always will be 0. The problem using the machine is that when it draws numbers from the standard normal distribution, it has to round off the numbers before it calculate the mean, and then we will have some problem with numerical precision, but as we see, it's almost 0 anyway. To further understand how the machine works contra the real math, please look at this comment which is written from line 69 to line 84 here. Okay. Then we are in B asked to standardize these x's, and to standardize we have to minus the mean and divide on the standard deviation. So therefore, to standardize the x's, I take the x's minus the mean of the x's and divide on the standard deviation. And now I got 100 standardized variables. And then I can take the mean to these standardized variables, and I can find the standard deviation to these standardized values here, and then we can print it. And if the math and it should be the mean of the set should be equal 0, and that's actually because if we look at the set, so we see that in the numerator it stands x minus np mean x, and that's actually tilde x, and we know that the mean of this one is 0, so therefore also the set has to be, the mean to the set has to be 0. And as I told you lastly, tilde x can be shown mathematically to always be 0. Likewise, we can show that the standard deviation of standardized variables in this example always will be 1. So therefore, when I print the standard deviation of these standardized variables, also we should have 1. But again, we don't get it exactly because of numerical precision in the computer. So then we go to 3C, and in 3C we are giving a formula. So let's look at this formula we are getting. So 3C. The formula is like this: the sum k equals 0 to n x k, and that sum should be the same as taking 1 minus x to the power of x n plus 1 divided on 1 minus x. So, and this one we can, and in this special example we get that n is equal 10 and x is equal 0.5. So this gives us that we are going to compute the sum k equals 0 to n equal 10, 0.5 in k, and that should then be equal to 1 minus 0.5 to the power of 10 plus 1 divided on 1 minus 0.5. Okay. So let's see if this is true. We could split, we can now think about this as the left side and this as the right side of the formula. And of course we could now use the left side to compute the sum. So on the left side which is, we could write this sum out and we then get 0.5 in the power of 0 plus 0.5 in the power of 1 plus 0.5 in the power of 2 plus 0.5 in the power of 10. And this gives a number. So how could we do that in Python? Let's do it first. So then we set n equal 10, x equals 0.5, and I also now here make a variable series equal 0. So series is now equal 0. And here left side of the formula, the hard way. That is what I showed you just in the notebook. We could find the sum by taking 0.5 in the power to 0 plus 0.5 to the power of 1 and so on. And we could compute this in Python and print the sum and look what it is. And that it's 1.999023435. So then I could write this in the notebook. Like this. So here you have the answer. So, but we could also compute this left side in a little more smarter way, which is pretty normal when programming. So I can do it through a for loop. So what I do is going through all the case in a for loop, and we know that the case are ranged from 0 to n. But a little remark here first is that if, for example, a is range 0 from 0 to 4 with steps with 1 steps, this range will start at 0 but ends at 4 minus 1 equal 3. So it actually is the number 0, 1, 2, 3. So in the for loop, I therefore have to say that I will go through the case from 0 to n plus 1. Because if I just put n, it will just go to 9. But if I use n plus 1, the last one I will get in the range is n plus 1 minus 1, actually n, which is 10. So this range is actually the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, and 10. And then what is this for loop doing? Yes, first time in the for loop, this number series is set to 0.5 in the power of 0, which is equal 1. So then series is being updated from being 0 to being 1. But after the second time in the for loop, this number, series, is now 0.5 in the power of 0 plus 0.5 in the power of 1. And then the number series is again updated. And after the third time, it is 0.5 in the power of 0 plus 0.5 in the power of 1 plus 0.5 in the power of 2, and so on. And this should give us, and after the last time in the for loop, series should be the same as the sum calculated the hard way above. So let's see if this is correct. So first I take this for loop. Of course I have to take this first, and then I can take the for loop. And then we could print now series, because that should be updated to the total sum. And we got exactly the same as we did the hard way. So now we have seen how we can compute the left side in different ways, but this is often take much more time than if we got a formula for the same sum. And in this exercise, we are told what the formula for the sum is. So instead of calculate the left side, we can calculate the right side of the formula. So let's do that in the notebook. So the point here is that we use the formula, which is actually this one, and this is the formula. We are going to use, and we can see that x in our exercise is 0.5 and n is 10. So let's calculate it. 1 minus 0.5 in the power of 10 plus 1 divided on 1 minus 0.5. And this should then be exactly the same as the left side, but it is pretty easy to write in Python. So here, then we check if the formula gives the right answer. It should, since the formula are proved mathematically. We haven't proved it, but somebody else have done it, and therefore we can use it. So sum formula is equal 1 minus x in the power of n plus 1 divided on 1 minus x. And with n equal 10 and x equal 0.5, n equal 10 and x equal 0.5, this sum should be the same as the left side, and we can see that's true. So if we go back to here, this is also equal, of course, equal 1.999023437. So it's pretty nice if we know a formula for the sum, then it goes very fast to compute it. Faster than anything else, especially when n is high. So that was exercise 3, I think. And then we can go to exercise 4. That's pretty much math, and we will be in the notebook. And we have to do it step by step. It takes some time, but the important thing here is that you understand every step. Do it again if you haven't made it before I do it. And then and you can do it again by looking at my notes, but after that you should try once more. Do it without the notes, because you have to do this on the exam too. So in exercise 4 we have the observations, x1, x2, xn, and let u, v be integers such that u is bigger or equal 1 and less or equal v, and v is less or equal n. And then we get the information we need to use later on, namely that we define the formula x bar of the observation from u to v to be equal 1 divided on v minus u plus 1. sum xi e equal u to v. So this is the real formula we are going to use later. Okay, but first we have to understand what this formula actually do. So recalling, so before we start the exercise, and we are told to do this, so we do it. Recalling that the mean of the n first numbers is equal 1 divided on n e equal 1 to n. That we know. We can easily deduce from the formula above that with u equal 1 and v equal n, xn bar is actually the same as x bar 1 colon n, which is equal 1, or we don't need actually this, we can actually just say we want to take the mean of the n of the numbers n to n, and this is x bar n to n. And if I use the formula now with u equal 1 and v equal n, we get 1 divided on n minus 1 and always plus 1. And then we get the sum e equal 1, because that's u, and v is n, xi. And then we see that this is actually the same as 1 divided on n, sum e equal 1 to n xi, which is the normal formula for the mean of the n numbers. So that should be nice. And we easily see, and we also easily see, using the formula, above, that x bar u colon u, which actually is to find the mean of the observation between u and u, but that is actually finding the mean of the only one observation, which is the u observation, and to find the mean of one observation, it should be the same as the observation. Let's see that actually is the truth by using the formula. So then we get 1 divided on u minus u plus 1, because here is u and vu. So it will be like this, and we have to take the sum from ei equal u to u xi, and we see that we get 1 divided on 1 xu, which is because the sum from u to u is just the one observation xu, and then we have to take this observation divided on all the observation, which is 1, and that is xu. And this is obvious. A. Suppose that A and B are integers such that A is bigger or equal 1, less or equal B, and lesser or equal, and B is lesser or equal N. In that way. And we are now told to show that, so what we're going to do now, show that xn bar can be written as the following: a divided on n, x bar 1 colon n, plus b minus a divided on n, x bar a plus 1 colon b, and in the end plus n minus b divided on n, x bar b plus 1 colon n. So this is what we are going to show. But to do that, we can see that in some sense we have to split up the observations in the A first, and then from A to B, and then from B to N. So let's start with the grand mean as we normally knew it, or how we know it. So the grand mean is like this, you all know. But let's now try to, and how can we write this otherwise? We could write this like 1 divided on n, x1 plus x2 plus x3 plus plus xn. And now let us do another thing, split it into parts, which is allowed, as you know. So we then got that this could be equal to 1 divided on n, x1 plus x2 plus plus xa plus xa plus 1 plus xa plus 2 plus plus xb, and then plus xb plus 1 plus, and then up to xn. So here we can think of this as the first part from 1 to A, this as the second part from A plus 1 to B, and this as the third part from B plus 1 to N. So this is then actually equal 1 divided on 1, sum of the first A x's. So this one is this one, plus, then I sum from A plus 1 to B. That is actually this one. And then we, in the last sum, the x's from B plus 1 to N, which is this one. So now we are a little bit closer to what we are going to show. We have split the data in 3 parts. That was necessary to do. So using the formula, so now using the formula x bar u colon v equal 1 divided on v minus u plus 1, sum e equal u v xi. which is, this can be rewritten if I now multiply both sides with v minus u plus 1. We get that the sum of the x's from e equal u to v is equal v minus u plus 1 times x bar. Be sure that you understand what I'm doing now, because we are going to use this in the rest of the exercise. So I just multiply me with v minus u plus 1, then I get v minus u plus 1 times x bar u colon v, and this other side, v minus u plus 1 cancel out, and we just end with the sum from u to v over xi, and I just changing sides here, so and that's okay. So then this is equal to this. So using this formula, we can now show that the sum xi e equal 1 to a, what must that be if I now use the formula? I'm now going to use this. Okay, we have to recognize that v is a and u is 1, so we get a minus 1 and always plus 1, x bar u, which is 1, colon v, which is a, which again gives a times x bar 1 colon a. So now we actually have showed that this sum can be written like this. And here u is equal 1 and v equal a, if you don't understand it. And we can also show that the sum over xi, I equal b a plus 1, to b is equal, and then v is b minus u, which is a plus 1, and always plus 1. Watch out for the parentheses here. X bar a plus 1 colon b, which is equal, we can see that the 1's cancels out, and we stand with b minus a times x bar a plus 1 colon b, like this. And here, of course, u is equal a plus 1 and v is equal b. So this one is actually the same as this one. And now we're soon in the end, but let's take the last one. The sum xi, I equal b plus 1 to n, xi equal, using the formula, with now is, here u is b plus 1 and v is equal n. So then we get v, which is n, minus u, which is b plus 1, watch up, plus 1, x bar b plus 1, u, colon n, v, which is equal to, because the 1's cancels out, n minus b times x bar b plus 1 colon n, like this. So, in other words, this one is equal this one. And what I'm going to do now is just to put these expressions into this expression. And then we will get what we are asked to show. So let's do it. Putting all this into xn bar equal 1 divided on n, sum I equal 1 to a xi plus a plus 1 to b plus 1 to n. We get 1 divided on n, and then we replace the sum of xi from 1 to a, which is this. So I write this one as a x bar 1 colon a plus, and we know that this sum is this sum. Another way to write the sum. So this is then b minus a times x bar a plus 1 colon b plus the last one, this one, so this one, which is n minus b times x bar b plus 1 colon n. And then we can just multiply 1 divided on n into the parentheses, and we get what we are asked to show. We then get a divided on n x bar 1 colon a plus b minus a divided on n x bar a plus 1 colon b plus n minus b divided on n x bar b plus 1 colon n. That what which was what we was supposed to show. So I think you will understand it when you go through it again, if you haven't understood it already. B, that's a pretty fast one. Let's why I do this all the time is I just have keep the screen in alive. Okay, B. We have in B we are asked if these three parts are computed separately. So we can write it if this one and this one and this one were computed separately on three equally fast computers, we should choose A and B such that we split the data or observations here in three equal parts. Otherwise, we have to wait for the computer assigned the most observations. Okay. So that should be pretty easy to accept. And then we take C. And in C, we are asked to show that, and what are we going to show? Yes, we are going to show that the empirical variance Sx in the power of 2 can be written like this. Yes. So what do we do then? Before I start, I say, remember that when A is a constant, sum over A xi, e equal 1 to n, is equal A times the sum A xi. No, I'm sorry. We can put the A or the constant outside the summation sign, like this, and sum over xi. So that's of course okay. And remember also, because I'm going to use it, remember that xn bar equal 1 divided on n, sum xi, I equal 1 to n, that this is equivalent, because I can just multiply with n on both sides, so we get that the sum of the xi's from e equal 1 to n is equal n x bar n. So this we have to know, and this we have to know. We're going to use that. And also I can have a remark here. Remark: given data, x bar n is a constant. Okay? Okay, so how are we going to show this expression? Because we actually don't know this from before, but what we know is this. We know that the empirical variance Sx in the power of 2 is equal 1 divided on n minus 1, sum e equal 1 to n, xi minus x bar n. This we know, that you learn also in high school or gymnasium. So this is a truth. And just by manipulating this expression, we will end with this expression. So it's just how to manipulate. and it's many ways to roam, but I now go this way, following way. I could write this, of course, like this, that you understand, and I can write this again as at times xi. I take this one with this parenthesis, so that I will get xi times xi minus x bar n, and then I take this one with this parenthesis, and I get then minus x bar n times xi minus x bar n, like this. So let's remove this. So actually we should have this one too. And then we can go on. I just multiply. So now I get xi times xi is xi in the power of 2 minus xi x bar n minus xn bar xi plus, because minus times minus is plus, xn bar in the power of 2, like this. And now I will let the summation sign get inside the parenthesis, which is allowed. So then I get this. Like this. And now I'm going to use the fact that x bar n is a constant. So now I can write this as I can now put the x bar outside the summation sign. Remembering that x bar n is a constant, like this, and also here. And oh, here I had to put the sum sign. Of course. So, and actually x bar n in the power 2 is also a constant if x n bar is a constant. So I can write this like this. But if I take all out, I have to put in 1, like this. So we are closer to what we are going to show now. So then we got that this is the sum xi in the power of 2 minus, and as the other thing we have to remember is that we know that the sum of the xi's can be written like this. The sum of the xi's can be written as n times x bar n. So let's do that. So instead of writing the sum of xi, I can write that as n times x bar n. So this one is this one. And here too, minus x bar n, and I know that this sum is the same as n times x n bar, plus, And this last one, I can see that I should sum 1 over, so I just write it very fast here, sum I equal 1 to n. 1 is actually 1 plus 1 plus 1 plus 1 n times. So this is actually equal n. So if I shall sum 1 n times, it has to be n. So this can be written as this. And now, 2 more lines. We now have this, and then we get minus n times x n bar in the power of 2. And the next is also the same. Actually, that's n times x n bar in the power of 2 plus, and the last one is also equal. So then I could add these 3 last expressions. And then I have minus 1 n x bar n in the power of 2, minus 1 more, it's minus 2, plus 1 is minus 1. So this is minus 1 n x bar n in the power of 2, like this. And then, if I now just multiply 1 divided over n minus 1 into the parenthesis, I probably get what I was going to show, because this gives n minus 1 sum xi in the power of 2 from I equal 1 to n minus n over n minus 1 x bar n to the power of 2. I may write this like this. So, what we was supposed to show. So what are we doing? We just use what we already know and manipulate on this expression to get the new way to write the empirical variance. Okay. Then it's a little shorter exercise, D, and the last one. So let's look at that. I think I'm going to write the sum here. Anyway. So what we know is, this is the information we get. That is that we know the sum of the xi squared e equal 1 to a, and the sum e equal 1 to a xi calculated on the first machine. And we also know, this is information we get, a plus 1 to b xi squared, and the sum I a plus 1 to b xi calculated on machine 2, and at last we know e equal b plus 1 to n xi squared, and the sum I equal b plus 1 to n xi calculated on the third machine. And the question is, can we just by knowing the information from the three machines given above, compute the overall empirical standard deviation. Okay, we know we know the formula for the empirical variance. That is Sx squared. And now I use the formula we have just derived. 1 divided on n minus 1, sum xi in the power of 2, minus n divided on n minus 1, xn in the power of 2. Like this. But if we know the empirical variance, we then also know the empirical standard deviation, which is Sx equal the square root of the expression above, minus 1, so this is okay, this is easy. But now, so the question is, can we compute this one just knowing this, just knowing this information here? If we know that information, we have green light for n minus 1 because we know n, and we therefore have green light for this one. We know n, so that's not a problem. But do we know this? Do we know this when we just have this information? Actually we do, because we also know that the sum xi in the power of 2, I equal 1 to n, is equal, because we can split the sum into 3 parts, and these 3 parts are the parts which the three machines have calculated. So this can be written as following. In the power of 2. And therefore we have green light for the sum of the xi's overall squared. The xi squared and the sum of that overall. And because we just used this information, and this information to compute the overall xi squared. And then lastly, we have to explain that we know this one too. Do we? Okay. We know that we know that xn bar is equal the sum of I equal 1 to a xi plus the sum or from a plus 1 to b xi plus the sum b plus 1 to n xi divided on n. That we know. That's equal to the sum of all the xi's divided on n. We just split the sum of the xi's in 3 parts. And since this is correct, we can compute this one. So, and therefore we have the x bar n2. We can compute it because we have the information of the sum over the a first axis and the sum over the a plus from the a plus 1 to the b next axis and the last sum from the b plus 1 to the n axis. Okay? Do you have any further questions now? Go to office hour or send an email. Okay, have a nice morning, evening, lunch, training session, whatever you are doing. Bye.